Well, welcome to the last official lecture of the semester. Again, just a reminder, tomorrow obviously is exam 3. Wednesday will be entirely review. Has anyone taken a peek at the practice test yet? It's really long. It's really long. And so we're going to go over that today. The lecture part of today won't be terribly long because this is not really complicated stuff, but I do want to spend a significant amount of time on the practice test because this exam will seal most of your fate. In other words, whether you have to take the final or not will largely be contingent on how well you do on this last test, and your goal is always to, well, avoid the final if you can. So Wednesday will be review. It's a less than a directed review. It'll be mostly, I'll be talking about the structure of the test and taking any questions and certainly going over the last quizzes. Okay, but it won't be, I'm going to sit down and teach you what we did for the entire course. That doesn't really make sense for a review. So you really want to come with questions. Of course, I'll have the exams and I'll give those back to you on Wednesday as always. And then Thursday, we're done, you know, and then you get, technically we say 5 weeks off, but it's really 5 weeks from the following Monday. So it's, 5 weeks plus a weekend, and that's why you took this course. Hopefully you're not taking like another 2 8-week courses that would make your summers really, really tough. Now, we're talking something called graph theory, which is really an ambiguous term, but we're starting with the very basics. We're starting with the introduction, and that's it. Where you would see this again would be in an upper division combinatorics class. And many of you, since most of you are either math or computer science, it's highly likely that most of you would take that. If you're a computer science, I think you have to take it. If you're a math, you don't, because in math you have choices. You have directions you can choose. That was a direction I chose in grad school, or actually as an undergraduate first and then in grad school. I absolutely loved it. Graph theory is just a small portion. What we've done for the last few weeks in chapter 9, that's a significant portion. So the idea of a graph is I have two things. I have vertices, and I have I have vertices, and I have what are called edges. An edge is anything that joins two vertices. A vertex itself is just a point. Now, if you think of polygons, okay, this is not in the textbook, but I think this is the easiest way to match them up. If I'm thinking of a polygon, okay, that's something simple like a triangle. Okay, a triangle is described by 3 vertices, and I also have 3 sides, but technically those sides are called edges. If we're in 3 dimensions, for example, if we're in 3 dimensions, because this is where it always gets ambiguous with notation, what we're doing is purely 2-dimensional, by the way. If I use the term side, what are you thinking?
Box.
Are you think? Well, no. If I said the side of the shape, are you thinking wall or are you thinking line segment? If I use the word side,
Wall.
neither, because you can't use side in 3 dimensions. It's a completely meaningless, ambiguous term. You never use the word side. What? How in the world would you know if I meant this if I said the word side? Because that's what we use in 2 dimensions. No, in 3 dimensions, this is called an edge, and this is called a face. You go, oh yeah, when you refer to the face of a building, you use that in common English. Because when you say side, it's ambiguous. In 2 dimensions, side is edge. In 3 dimensions, side could be either one, therefore we don't use it. We never say sides. We say how many faces. So if I said a cube has how many sides, you'd go, well, it has a whole bunch of edges. It has 12 edges and it has 6 faces. So if I said how many sides, you go, which one do you mean? So we'd say edges or faces. So what we're going to do is just not use the word side, we're going to use the word edge. Now, there's no ambiguity, but someone might say, well, wouldn't this be a side? The whole front of it? Do you see the problem with ambiguity? We use the language to have multiple meanings, therefore, that's probably a word we don't want to use. Because if I'm speaking and you're actually having to think, well, what's he referring to? I'm not sure which one he's saying. Then it's probably not a good term. So in any polygon, we describe a polygon by the number of vertices or the number of edges because those must be the same. So what do we say a triangle is a 3, quote unquote, sided figure? But if I said it has 3 vertices, aren't I saying the same thing? 3 vertices joined by 3 edges. So an edge is a line segment that joins vertices in a polygon. And a vertex is something that is adjacent to two edges. Goes both ways. Now, in graph theory, an edge has to come from a vertex. An edge can't just live by itself. It has to have vertices no matter what. But strangely enough, a vertex doesn't have to have an edge. I can have a vertex just sitting on its own. It's kind of boring, but that's a legal move, okay? So that's a strange thing. So if I'm describing a figure, let's say I'm describing something like this. We'll keep it really simple. I'll call that V1, V2, V3, and E1, E2, E3. I'm describing the vertices and the edges. Now, the edge, when I describe an edge is always described by what vertices is it involved in. Okay, so the first thing I would do, I would say edge 3 involves V1, comma, V3. I'm writing it as a set, not an ordered pair. Now think about this for a moment. Why am I writing it as an ordered pair? Excuse me, why am I not writing it as an ordered pair?
Because there could be multiple connections to that vertex.
Well, just basically, I'm going to keep my picture simple. If I wrote it V1, comma, V3 as an ordered pair, doesn't that mean I have to start at V1 and end at V3? I would have to go in an order, wouldn't I? But is there anything wrong with me starting at V3 and ending at V1? Is there anything wrong with that? No. No, so we write it as an ordered. Right now, we don't write it as an ordered pair because we're saying, I'm not indicating where I'm starting and finishing. I'm just indicating what vertices are involved. That's it. It's like, oh, okay, that's pretty simple if I think of it that way. Now, part of the reason I did that was because there's nothing wrong with me doing this. Ooh. Could I have something like this? Could I have multiple edges using the same vertices? Yes, I can. And the simplest way we're going to describe it, think of this as you're hiking. These are trails. Is there anything wrong with two different ways of getting from point A to point B when you're hiking? You could take that path or you could take that path and you get to the same place. So there's nothing wrong with this, and E4 would involve the same sets of vertices. Okay, so there's a perfect picture. Now, could I have a vertex like this? In fact, I'm going to include this in this picture, and I'll call this one V4. All of this together constitutes a graph. Vertices do not have to have edges. Edges do have to have vertices. Okay, that's a fairly simple concept. Okay. Now, can I have a graph with direction? Yes, because that's something we're going to be able to do. Because I want to be able to describe directions. There's vocab in the book. It's a little confusing. There's a walk. There's a path. There's a trail. There's a circuit. And they're not exactly the same thing, but we try to match words. A circuit, think of as a loop. The word circuit is perfectly. How many have ever trained in a gym for any length of time? You went to a gym and worked out. Okay, what is circuit training? Let me know. It's the same use of the word circuit.
Like you're going from one workout to another. Like there's a bunch of different.
But what are you always doing?
Going in a loop.
Repeating.
You're coming back and repeating that loop. And in fact, you're not only repeating that loop, you're repeating that loop in that order, aren't you? Okay, so when we talk about circuit training, maybe you're doing a bench press, and then you're going over here and doing some squats, and then you're going over here and doing some deadlifts, and you're going over here and doing some pull-ups, and you're pretty exhausted after 5 minutes. But you've decided to do this loop. That's called circuit training. I'm not doing one exercise and then moving on to a second. I'm doing all of them in a loop. So that's why it's called circuit training, because I'm actually completing one circuit when I've done all the exercises. And then I do it again and again. We're not interested in the repeats. We're interested in, I've done one circuit, which means I've done one complete loop. All that means is I'm going to end up where I start. That's it. That's what a circuit is. That's what I want you guys to be aware of, is the circuit part, more than the other words. There's a lot of vocab, and some of it is just not terribly important. It builds up to it. So for me to have a circuit, I really need to have direction. So let's say that I wanted to go from V1 to V2 in this direction, V2 to V3 in this direction, V3 back to V1 in this direction, and then V1 back to V3 in this direction. This would be my trail, okay? This wouldn't technically be a circuit. Why? Why would it not be a circuit?
Because it's not a loop, there's multiple directions.
Well, where did I start? And where did I end? So I didn't end where I started. Did I cover everything? Did I hit all the edges and all the vertices? Yeah, but I didn't end where I started. A circuit's got to end where you start. But I want to describe this. So now how do I describe E1? I now describe E1 as an ordered pair. Why? Because I'm saying most specifically, I'm starting at V1 and I'm ending at V2. I'm not going the other way. So this is what is called, this guy here is called a directed graph. That's it. The other one was a graph. This is called a directed graph because I'm actually indicating what directions I'm going. So it'd be kind of like saying, all right, you're a business traveler. By the way, this is one of the places where this is used. And I use this in Calc 1, this analogy, all right? You're a business traveler and you have an itinerary in front of you, and let's say you're starting in San Diego, and over the next month or so, you have to visit New York City, San Francisco, Boston, Seattle, Atlanta, Portland, Philadelphia, and let's just throw in, Sacramento. Oh, and then, of course, Hartford, Connecticut, and then LA. So of course, and you're a business traveler and you want to optimize. So of course you're gonna do the East Coast, West Coast, East Coast, West Coast, East Coast, West Coast, right? Or maybe you're starting in San Diego, go up, hit all the coast in Seattle, go across, hit them all down. Now think about that logically. Wouldn't that make a lot more sense? Because you are minimizing the distance traveled, which automatically means minimizing the time spent, which also severely minimizes the money it's going to cost. Does that make sense? So you're a business traveler, so I don't want to be flying back and forth. I want to do a loop. So I want to create a circuit, but eventually I want to end up back here. Because if I end up at my last stop, not only is it not a circuit, right? That means I'm now going to spend the rest of my life in LA or where. No, I'm coming back home. So you'd say optimal travel, I'm going to start here and every one is going to be directed. I don't just have a bunch of random vertices, because if I put all the vertices down, which represent cities, and I put edges between every city, then that would indicate all the possible routes I could take. Do you agree? But it would not be efficient, and I'd find myself backtracking and doubling up. One of the things we try to avoid, not the same vertex twice. We try to avoid the same edge twice. You with me on that? We try to avoid repeating edges whenever you're coming up with a situation here. So I did not repeat an edge. So I want to describe this path. And so the way we usually do it, where did I start? I went V1, E1, V2, E2, V3, E3, V1, E4, V3. This is the mathematics we would use to describe this path. We simply write them all out. Now it's obvious not only where I started and where I end, which edges did I use, because obviously right here there's a little ambiguity, because I had two possibilities, so I clearly indicate them. Now, a simple term, but a very important term. In a polygon, every vertex has exactly two edges that come out of it. Do you agree? So we would call these edges adjacent sides, or adjacent edges, because they share the same vertex. And the term adjacent is a very important term. What does it mean, just in general, the word adjacent? Because people use that in the English language all the time, but it's often misused. What is it? If you were using just an English language.
Next to.
Yeah, that's probably the simplest way to describe it. But how many here live in an apartment or condominium? Okay, do you share a wall with any of your neighbors? Yeah, it's always the loud ones, right? You share a wall, so you would have adjacent units. I have a neighbor that lives next door to me on both sides of my house, but we don't share any walls. But we do share a fence. So we have adjacent backyards because our backyards share a fence. We do not have adjacent houses. Now, next to is a good starting point, but I changed the rules a little bit. My backyards are adjacent with my neighbors, but my houses are not. You people who live in condos or apartments, you are adjacent to your neighbors. Some of them. What is the commonality in both cases?
They're touching.
We share
You share, I like it, you share
an edge.
an edge or a border of some sort. Does that make sense? So if you have an adjacent condo, that means you are sharing an actual border. Next door neighbors, you're not sharing anything necessarily. They're just the closest house to you. But an adjacent yard, we share a fence. We share the actual border itself. So is anybody here technically adjacent to anybody else in the classroom? No, because you're not sharing a border. There is something between you, right? There's like an alleyway. That would be kind of like saying I'm adjacent to my neighbor directly across the street. No, their proximity is close, but we don't share anything. So we would not use the term adjacent. So in this case here, we always say these are adjacent sides because they share the vertex. In a rectangle, okay, would we say these are adjacent sides? No, actually we use a different word. It's real simple. We'd say they are opposite. We say, oh, okay, they're opposite sides. Now that gets a little bit confusing if I have 5 sides, because technically neither one of these sides are adjacent to neither one of these sides are adjacent to this one. So we loosely use the term opposite because they're not adjacent. But is it directly opposite? No, but people that live on the other side of my street live on the opposite side of the street. But the entire street would house all the people who live on the opposite side of the street. There doesn't have to be one house, does it? Doesn't have to be the house that's directly. What about the ones next door to that and next door? So we use the language not loosely. No, we want to make sure we categorize things really simply. So adjacent means you share something. So edges, any edge always has 2 vertices. Any vertex does not necessarily have to have an edge. Okay? Okay, it can stand alone. Now, would we say these 2 edges here are adjacent? These 2 right here? Yeah, because they share that vertex. So we want to use that word appropriately. So now, I want to describe something called the degree. This one is actually really important in the big picture. The degree of a vertex is simply how many edges are leaving that vertex. So if I ask you for the degree, this is V2. I want the degree of V2. And we often just write it, degree V2. We're not really clever. What would you say that is? 2. How about the degree of V3?
Okay.
3. How about the degree of V4? 0. Good. And let's go back to the beginning. How about the degree of V1?
Also 3.
Also 3. So if I add those up, I get 8. Okay, great. I have 4 vertices of varying degrees. I have 3, 2, 3, 0. Those add up to 8. Big deal. Actually, it is a big deal. 8's an even number. I'm going to show you, if I add up all of the degrees of any graph, it has to be an even number. Interestingly enough, it has to be even. So there's something called, the way, the proof of this is just, it's so cool and it's so ODA. It's called the handshake theorem. Okay? Now, we're going to make one simple assumption. You can't shake your own hand. That doesn't count. Right? Is everybody okay with that? You can't shake your own hand. So in a group of people, doesn't matter how many people you have N people. And everybody in there is going to shake somebody's hand, or they're not. Doesn't really matter. So Benito's like, no, I'm not touching anybody. I'm a germaphobe, right? And Matthew's like, no, I want to make more friends and add them to my Instagram account and all that stuff. So it doesn't matter how many handshakes you have, but every time you shake somebody's hand, you are an edge, in a sense. And the hands themselves, you can think of as the vertices. So if I'm shaking your hand, there's an edge, and our hands are kind of like the vertices. Does that make sense? You can't shake your own hand, so doesn't every handshake automatically involve two people? Now think of this logically. Every handshake that can possibly happen. So at the end of the day, I ask each of you, how many hands did you shake? And you tell me how many hands you shook, you tell me how many hands you shook, you tell me how many hands you shook. Because some of you shake an odd number of hands?
Yes.
Absolutely. Absolutely. Everybody here could shake an odd number of hands. So could there be an odd number of handshakes? Sure. Yeah. In fact, nobody here shook anybody's hand except Zachary, and you shook Mandy's hand, because you have to have a partner. Okay? So how many hands you shook, think of as the degree of your vertex. You with me on this? How many hands you shook is the degree of your vertex, because when you shake somebody's hand, that's an edge extended. I shook 3 hands today, so my vertex has degree 3. But that also means if I put all of you down as dots, all of you are vertices, and I connect all the people that shook hands. Okay? All the people that shook hands. Then the degrees of the vertices must be even, because the degrees of the vertices must be exactly twice what? The number of handshakes. Because every handshake has to involve 2 people. So you and I shook hands, so now there's an edge joining us. You shook hands with Samuel, that's it. So your degree is 2. I may choose not to shake anybody else's hand. Samuel may choose not to shake anyone else's hand. That's fine. But there were 2 handshakes altogether, and our vertices had degrees 1, 1, and 2. You with me so far? So the vertices, there were 4 vertices, there were 2 handshakes. Every handshake has to involve 2 vertices. Could you go back and shake somebody's hand a second time? Sure. Yeah, you're real friendly, and you have bad memory. You can't remember if you shook their hand or not. So every time there's a handshake, there's an edge and 2 vertices. So no matter what, there must be twice as many vertices as there are edges, because each edge has to involve 2 vertices. Each handshake has to involve 2 people. You can't have a handshake only involve one person, because that would mean you're shaking your own hand, and that we said was not allowed. So no matter how many vertices I have, so the vertices, let's keep it simple. And you decide, okay, well, let's test this. So this person shakes this person, and they shake this person. And this person's going to go here and maybe here. And this person here, no, they're done. This person here is going to go also here. And this person here says, that person there, I want to include them. I'm going to do that. Let's have some fun. Every one of these, think of as a handshake. So this person shook that person's hand, that person's hand, that person's hand, that person's hand. Great. If there are n vertices, let's start really simple. Let's say you don't shake anybody's hand twice. Let's keep it. If there are n vertices, then or n people, what's the most number of handshakes you could have then?
N-1.
N-1, because you're not shaking your own hand. If we allow for doubling up, that's okay. I don't want to do that because that makes it too confusing at first. The most anybody could have is N-1. Oh, by the way, Samuel quickly joins the party and is sitting here and he's like, hey, well, I'm here. Can I have a vertex that doesn't shake anybody's hand? Yeah, like say germaphobe, whatever. Nothing wrong with this. What's the degree of this vertex? 0. What's the degree of this one? 2, this one? 4, this one? 3, this one? This one? How many handshakes, exactly how many handshakes took place? We'll count the line segments. Edges, sorry. An edge, by the way, doesn't have to be straight. It's however you get there. So I have 1, 2, 3, 4, 5, 6, 7. I think I counted right. I have 7 edges, and what is the total degree? 14. Surprise? No, it's exactly what we just said. The degree must be double the number of edges, because the edges represents a handshake took place The vertices are the two people involved in the handshake. So that's why this is called the handshake theorem, because it makes perfect sense. Okay? So, let's see. I think I asked one of these, oh, I can't remember if I asked this or not. Hold on. Let me look at my practice test for a second. I hopefully asked this on the practice test. Give me 1 second to bring it up. Because we're going to go over this later. It's not a trick question once you understand the handshake theorem. Oh, I don't think I asked it. Oh, darn. Oh, well. Every edge can have any degree possible. There's no limit to the, you know, I'm sorry, I said it backwards. Every vertex can have any degree possible. A vertex can stand alone, I can join every other vertex. I can even, you know, do this multiple times. So when I ask for the degree of a vertex, that does not have to be even. That's a common error. It's the sum of all the degrees have to be even, and the sum of all the degrees should be exactly double the number of edges. Because every edge joins two vertices. So if I have 10 edges, I have to have 20 vertices. Or do I? No, I have to have degree 20. How many edges do I have?
4.
How many vertices do I have? 3 here. Let's ignore this one for just a moment. The number of edges don't match, it's the degree of the vertices have to be double the number of edges. And we went back and said the degree was 8. Did I count that right? The degree was 8, and you had 4 edges. That's exactly what we were saying. The degree of the vertices has to be exactly twice the edges, not the number of vertices, because there's nothing wrong with doing this. Okay? Do you see why that can be a little bit confusing at times when I'm looking at things? So, let me ask you. This is where it gets kind of fun. This is a simple question. I want you to draw a graph with 4 vertices having degrees, having one, 2, 4, and 3. Right now, do that on your own. Draw a graph where your vertices have these 3 degrees, or these. So you have four vertices altogether with the following degrees.
Do they matter, like the order?
Well, that's, just draw a graph. We'll label it later. You can label it now if you want. You can just put down and call them V1, V2, V3, V4. But I want the picture. Now here's the cool part. There are an infinite number of representations. Some of them will be what we call topologically equivalent, or in this concept, isomorphic. They will literally be the same thing. For example, let me give you a simple. Let's suppose that Zachary draws this, okay, and Mandy draws this. You just drew the same thing. These are not different. Everybody understand? These are not different in any way. Just simply turning it on its side, I still have the same thing. So sometimes we can draw something that's the same. So I'm going to put 4 vertices down. Just make it easy on myself. Could you put all 4 of these vertices on the same line? Absolutely. So I'm going to do that as a second representation, just to show you. Representations are not unique. Okay, so I have degree 1. How can I get degree 1? Let's call that V1. Now it has degree 1. All right. Now, this guy needs degree 2. That makes it kind of easy. What am I going to do next, probably? There. That has 1, that has 2. The next one needs degree 4, and that one needs degree 3. We got a problem there. I can't join this one to either one of those, can I? Oh my goodness. How am I going to do this? Well, let's start by doing this. And then how about that? I don't have to have them in order. I can make that one the 4. I got my 3. You're gonna like this one.
It's a straight line between.
It can come back to itself. That seems crazy, but totally okay. Wait, how do I have degree 4? How many edges are leaving the vertex? So if I draw a little circle around the vertex, how many different things do you see leaving the vertex? You actually see 4. So I can have a loop back to the same vertex. It's one edge and it would have degree 2.
So in the handshake theorem, you said you can't shake your own
Well,
hand.
no, that's how we prove.
Five.
That's how we prove the theorem in general. That's how we prove the theorem in general. Saying if I say that, then we've actually said it in any case. So now if I allow a loop because you said, but there's only one edge, but there's 2 different ways I'm leaving it. It'd be kind of like saying you're going to go out that door and come back in this door. You did a loop. There's 2 different ways I could leave that, but we're going to call the classroom a vertex. Could you come out and come back in the classroom? There's nothing wrong with that concept. The handshake theorem, we start by saying you're not shaking your own hand because it makes it ambiguous when we're talking about, joining. If you and I shake hands, there's clearly one edge and 2 vertices. If I shake my own hand, it's a little confusing. But once we've established that, now if a vertex has a loop that comes back to itself, I probably should use a different color here. If you count, so if I have this situation here, we'd say there's one edge, but there's 2 different ways this edge is coming back into the vertex. See, when I'm looking at this, I'm not looking where they came from. What am I looking? There's 2 ways an edge is coming into the vertex. Didn't matter where it came from. There's one way an edge is coming here. There's 3 ways. So I've just drawn a graph that has these vertices. You can put them in any order. Now what I'd like to do is do the same thing here. Do you think that's easier or harder? Or would you say it's the same? I got my 1 and my 2. Clearly I got to join these guys. Now what? I do the same thing I just did a moment ago? Does that work? As it turns out, we would say these graphs are what we call topologically equivalent. Now that's another course altogether that does use common occurrence. Has anyone ever heard the term topologically equivalent? It's kind of a weird thing. What context?
Like some shows like a donut and a coffee mug or something like that.
Perfect. Yeah. A donut and a coffee mug, they both involve a torus. In other words, the coffee mug has a handle, but it has an open interior. So imagine you're molding it with clay. I have a piece of clay and I'm just keep pushing it down and creating a crater, no holes. But the handle has to involve a hole. The donut has to involve a hole, doesn't it? So they're called topologically equivalent. Isn't that weird? But if I have a cube and I have a pad of paper, they're topologically equivalent. Because they're both just one lump. I can flatten out the cube into the pad of paper. There's no holes. So a lot of times we think about it in terms of holes. How are these topologically equivalent? I don't know. What if I bend this here? And then, you understand, I can just bend things and make them kind of, they're kind of the same. Now, I could have put the 1 or the 2 somewhere else. That's irrelevant. The whole point of that problem is to show you not only is it easy to come up with an answer, but answers are not unique. Okay, similar problem. All right, now let's do one where it's, oops, dead pen, a lot of those today. I want you to come up with one where the vertices are 2, 4, 1, and 6. Now, if I have a vertex of degree 6, obviously I can have more than one loop, can't I? So if I did this, would that vertex now have degree 6? And by the way, do I have to attach it to any other vertices? No, I don't. I can actually leave it all by itself. So I covered the 6 by doing that. So, what do you think? Anybody got an idea? Samuel's already given up on the idea. Samuel, why'd you give up so soon?
It's odd.
Because the sum of the degrees is odd. That means it is not actually possible. Whoa. Now that's cool. You just told me that's impossible, and you're right. The sum of the degrees had to be even. Now there's a lot of ways I can get the degree 6, that's all well and good, but that question is impossible. So you quickly do a check and say, nope, can't do it. Imagine, if you will, you have 4 people. Okay, the 4 of us, and we're going to shake hands all over the place. Now I can shake your hands as many times as I want. Okay? And in the end we said, oh, between the 4 of us we had 13 handshakes between us. That's not possible. Because every time 2 people shake hands, there's an even number of handshakes. Again, does that make sense? Oh, okay. Now, I said this didn't have to be attached. These are attached, these are attached, these are not attached. So we're going to use the term, one more new term that's kind of an oh duh. Connected graph. What do you suppose that means, without even me telling you? If I said I have a connected graph, I'm going to give you a hint. Connected graph, not connected graph.
You can reach every point.
Yeah, every vertex is connected to at least one other vertex by an edge, and you can get from any one vertex to another. Now be careful. If I said every vertex is connected to another vertex, that statement is true, isn't it? Each of my vertices is connected to another vertex. But this would not be a connected graph because I have 2 completely separate sections. Oh, so there must be a path to get from any vertex to another. So for this to be a connected graph, what must also be? I must have another edge somewhere that joins the 2 individual sections. Everybody go with that? That's kind of an oh duh. Excuse me. That's kind of an oh duh, but it's an important oh duh. Now, the most important type of circuit would be a circuit that hits everything, but hopefully doesn't repeat things. Now think about this logically. I want to hit everything but not repeat things. Oops. Okay, so I want to get from each vertex to the next vertex and then back to the start. Well, let me start simply. I want to go from each vertex. Let's start with it. I have 2 vertices. I want to start here and end here. What do you think? I think we agree it's pretty simple. Okay. Oh, okay, so let me just create a box. Great. Oh, except for one other thing. I want an edge joining each vertex. Okay. I don't like that one. Because that's not a vertex, but my edges cross. Is it possible for me to do this and have an edge joining every vertex and not have the edges cross? This is actually one of the most important real life problems that exists, believe it or not. Let me know a simple example of this kind of thinking. You have neighbors, and up in the air, you have what? Telephone lines.
Oh.
But you have telephone lines. So we're going to go back. How many, when you were kids, you ever did the whole thing with the can and the string? Anybody ever do that? You have the can. I have a tin can. You have a tin can. We have a string. We talk to each other. It actually works to some degree. The string carries the vibration. And none of you ever did that as kids? It's cool, but only for a short distance. And I think really you could hear me talking anyway. So yeah. So we do that. So everybody has strings that go from one house to all your neighbor's house, but you don't want your strings touching. Because if your string's touching, that would affect the vibrations and you might not be able to hear anything. So is it possible for me to draw this and not cross any lines? I want an edge join, right now an edge joins every vertex, but I don't like the configuration. Okay? An edge joins every vertex, but I don't like the configuration. Excuse me. Now, I don't need the arrows, by the way. I really don't need the arrows. I just showed you if I wanted to start and come back. So if I just have vertex and edge, I just have vertex and edge, okay? I just have vertices and edges. Is it possible? You know the answer, because you probably all did this as kids. You played games like this, can you connect them all without crossing over any of them? Did anybody ever do stuff like that as kids? Little puzzles in a magazine, maybe?
Let's go outside the box.
Go outside the box. Did I complete my task? Yes. This is called K2, this is called K3, you're never gonna guess what this is called.
K4.
Oh! K stands for Kuratowski. The author gives some mention of him in the textbook, but not for this. He's actually one of the most important figures in graph theory. He actually lived, I think he died in 1980. So it was interesting, when I was in college, we studied this stuff. He had only, I'm dating myself, he had only recently died when I first learned this stuff, and he was still considered, you know, really, really important. Now it's a long time ago, but K5. This is where it gets really interesting. You're gonna like this. Okay. Can you draw a graph where every vertex has an edge to every other vertex, like I just did in 1, 2, and 3, or excuse me, in 2, 3, and 4? Can you do that without crossing? Yeah, let's do it. Let's start easy. This is kind of the easiest way to start. How about this guy? So far so good. And now we're to this guy, and we're to here. Can I get from here to here? No. And by the way, this is considered really huge. If I have a big graph, do you see K3 in this graph? Yeah, in fact, how many examples of K3 do you see in that graph? It's not a trick question. 4. Pick any 3 vertices and you have K3. Pick any 3 vertices. Maybe I'm gonna pick this one, and this one. Maybe I'm gonna pick this one, and this one. Maybe I'm gonna pick this one, and this one. Any 3 vertices you see were connected, you see K3. K3 is called a subgraph because it is within K4. Is K2 a subgraph of K4? Yeah, several of them. Is K2 a subgraph of K3? Yeah, 3 of them. So if a big graph has subgraphs of a particular nature, now, turns out, you're right, this is called K5. This is one of the things I remember learning in school. Let's suppose I have a big graph. I have lots of vertices and lots of edges. If there are any subgraphs that are K5 or higher, well, I just need K5, then it's not possible to connect every vertex without edges crossing. Now, why is that important? Well, think something as simple as phone lines. Okay, pretty much every house that was built for a long time had landlines. Forget cell phones for a moment. Every house had landlines. But what's the problem? Your house has to be connected in every direction in a sense. So what did that mean? That meant lines had to cross, or we had to do them at different elevations, didn't we? So what did they start going to? Oh my gosh, it might be as far back as the 80s and certainly by the 90s. Do you see a lot of brand new telephone poles in the United States? No, you don't see any new poles. What's happening over time? We put them underground. And we don't put big old heavy lines. It gets better, right? Fiber optics. You've heard the term fiber optics? That refers to the lines that are going underground very specifically. And it's better. right? Those are dangerous. Those, lightning storm, they fall down. But the idea being, I have to do things at different elevations because I can't have the lines cross. Now, I'm really using a simple example because you say, wait a minute, there's more than 5 people or 5 houses. Right? We have bazillions. So the idea is, if I have a subgraph of K5 or higher, there's no way to do this. Isn't that crazy? Now, Kuratowski was the one who mathematically proved that stuff. That's why these are called these guys. Now, what if, I like this example. This is my side of the street, these are my neighbors. Okay? I want to be able to connect to my neighbors. I don't care about connecting necessarily to the people next to me. I want to connect to my neighbors. So if I connect to my neighbors across the street, so far so good? What about that guy? Not so much. This, you notice I'm not connecting to the guys on the same side of the street. I want you to think about it literally as opposite sides of the street. This is what is called a bipartite graph. Okay? And all that means is that I've broken it up into 2 pieces, and I'm connecting one set of pieces. I'm connecting one set of pieces to another set of pieces. So let's start simple. And we give it a different name too, by the way. Boring, but legal. Yes, I have mismatched on purpose. That's important. Now, I'm going to draw them crossing because that's a legal representation. My question is it possible to draw this one without them crossing? That's the question. When we draw a bipartite graph, we usually draw it with all the edges crossing because we just want to know how many edges. My question to you is it possible to draw this without the edges crossing?
Yes.
Yeah, like the square going around. Do you agree? I could go around instead. So instead of that one, I could have gone like that. Well, we have a really clever way of naming these. What do we call this one? I didn't finish it. Once I connect all the vertices. So I'm going to go back to the picture. Now let's go ahead and connect the vertices and not worry about crossing. Hopefully I did that well. All right. My question was, this is K22. Could I have drawn it without the edges crossing? You said yes. What's this one called then? K33. Can I draw this one without the edges crossing?
Yes.
And oh, that's not it. I erased it. We tried it and we couldn't. Actually, we can't do K33. So there's another major piece. These are the 2 pieces I remember learning when I was in school. K5, if you have a subgraph of K5, you can't come up with it without the edges crossing. If you have a subgraph of a bipartite graph, that's K33. See, could I have K2020? K1000? Yeah. But if I have a K33 in my subgraph, which obviously any number bigger than 3 and 3 would have that, this is a subgraph, it's not possible to draw them again without crossing. And again, that creates a problem when I'm trying to actually make physical connections. So the example that was always used in my lifetime was phone lines. That's kind of archaic now, isn't it? Phone lines. But are there other things that maybe we have that might be an issue? Yeah, there's certain things that can't go overhead, and can't be made fiber optics, you have a toilet at home, don't you? Give me a simple example. Every house has these going out to the street, under your house, under the street.
Sewage pipes?
Sewage lines, yeah, sewage. Oh, yeah, could that present a problem since every single house has sewage lines going out? Yeah, you would want to make sure they don't cross. So, well, why would they ever cross? Well, I have a big house. By the way, my house has more than one. We just did a huge remodel. There's basically one coming out of every bathroom. Just giving you a heads up. And I really don't want them crossing. So in other words, when we're designing things, we have to take perhaps this into account. But it's kind of cool. This is K33. How many edges are there? Well, let's start here. How many edges?
4.
How many edges here?
9.
You see a pattern. Hopefully you do. By the way, 2 giving you 4 doesn't help. Why? No, you can't use that one, right? Because there's 3 ways I can get 4 using the numbers 2. But there's only one way I can get 9 using the numbers 3. What does it appear that's going on here? What is the degree of KMN? M times N. Yeah, that's what I wanted you to see. Oh, okay. Now, bipartite graph. Remember, I'm not doing any of the vertices on the same side. So here, the orientation and the setup actually is important. Okay? Because I need to be on opposite sides of something to be able to do this. Now, these are just simple definitions. There's nothing really tremendously clever about this. So if I asked you to draw this, you could. Now, if I said K with a single number, think polygon. Keep it really simple. Think polygon. And then just connect every vertex of your polygon. That's it. So if I said K4, think of a square, it could be a rectangle, but think of a 4-sided figure, and then I'm just going to connect every vertex. My question before was, is there an isomorphic representation that didn't have things crossing, and you were able to come up with one? But the theory is, and you don't have to prove this, this is a theorem, that K5, you can't do it. You can draw the vertices and draw the edges easily, but they're all going to cross, aren't they? And I can try going around and doing all sorts of clever things, but at some point, they got to cross. So we usually just bite the bullet and just make it cross early on and say, okay, can't do more. Now, is everybody cool with that? That's a pretty simple concept. So the bipartite and just the regular, the K is very specific, okay? So I have, let me go back to K 3, 4, 5. Now, I used the term degree of the graph. I kind of snuck that in. We said the degree of K33 was 9. But what was actually 9? There were 9 what? Edges. And the degree of the graph is the number of, right? It's the degree on each vertex, which means I'm counting. But did I actually have a degree? Did I actually have that degree?
No.
No, the degree was what? The number, I should say the number of edges was 9, sorry. What was the degree though?
18.
Yeah, why?
Because there's twice as many.
Because we counted edges, we didn't count the degree of the vertices. So very specifically, we should say the degree of the graph is simply twice that number. So what's easier to do? Count edges or count degree of a vertex?
Edges.
Tell me about each vertex.
I have 3.
Each vertex has degree 3. How many edges do you see? 6. So there are 6 edges, but the total of degrees is 12. So I was a little bit off. I said MN, Now I think you know what the answer is. What is MN? That's the number of edges. I left a space there. Well, not a very big space. MN is the number of edges, so what's the degree of the graph?
200.
2 times. We're showing it. Oh, okay. What's, like, this is going back. What's easier, counting the number of edges or counting the degree of each vertex? Keep going. This is K8. I want to do this for every single vertex. I want you to draw them. And then you're going to count up all the vertices, and then you're going to count up all the edges. And do you want to do this one? I don't want to do this one. We're trying to come up with a simpler way. That's the bipartite graph. Now I'm just going simple K whatever. Okay, well, I guess we could bite the bullet. Is it possible that you could leave out an edge when you're drawing all the edges? Is it possible you could accidentally leave out one? Yeah, you could. I don't really want to do this because it's going to be really long. Is there an easier way? I have 8 vertices, and there's an edge leaving every vertex going to every other vertex. What is the degree of that vertex then?
7.
7. How'd you get 7?
Because it can't intersect with itself.
Yeah, we're not doing loops. We're only doing edges to other vertices. That's the definition of this type of graph. Oh, so then the degree of K8 should be what? 8 times 7? Because there are 8 vertices, and you just said each vertex has degree 7. So let me go back. What's easier, counting the degrees of the vertices or counting the edges? Counting the degree of the vertices. At the beginning, you said no counting edges, but as the number of vertices increase, the number of edges is too hard to keep track of. So if I said, what's the degree? What is the degree then of Kn? This is a cool formula. N times n minus 1, exactly. Cool. Now, if this were a polygon, and by the way, there is geometry in this, and what I don't like doing is changing vocab when we change concepts. Because if I'm drawing a polygon, we still call this an edge. It's okay to call it a side, but if you're in my class, I'll actually call it an edge. What do we call that guy? Geometry. A line segment joining any 2 adjacent vertices. These are called adjacent vertices because they are part of the shape. These are not adjacent vertices. We use the term quote unquote opposite. Opposite is kind of vague. Why? Because what if I have 10 sides or 20, you know. But what do we call a line segment joining any 2 non-adjacent vertices? In any polygon, it's called, look at the end, starts with a D, ends with diagonal. Oh, you know that term. A diagonal is any line segment joining 2 non-adjacent vertices. So if I have, there's a hexagon. From this vertex, how many adjacent vertices are there? From that vertex right there. How many adjacent vertices?
4.
Adjacent.
Oh, sorry.
2. Because those are the only ones that are actually on the shape itself. Now, how many line segments can I draw from that vertex that are not 2 adjacent vertices? Well, there's one there, there's one there, there's one there. Do you agree? All 3 of those are called diagonals in a geometric figure.
Because it's opposite.
Because they're non-adjacent.
Non-adjacent.
So, in any, we'll call this an n-gon. That's what I like calling it. N being the number of sides, there can only be 2 adjacent vertices. Agreed? How many non-adjacent vertices are there in every n-gon more than 3 sides? This doesn't work for a triangle because all the vertices are adjacent. Well, it actually technically does work for a triangle, but
N minus 2.
10 minus 3. There's n minus 3 diagonals. Why n minus 3? Well, you're the one that said there were n minus 1 edges that I could leave that vertex with. But if 2 of them are already taken by the outer part of the polygon, then n minus 3. In a triangle, how many diagonals are there? In a triangle?
0.
None. 0. Oh, n minus 3. That makes sense, doesn't it? And a square from any one vertex, in a square, how many diagonals can I draw from any one vertex? Only one. That's the only diagonal I can draw from that vertex. So that would be n minus 3 diagonals from any vertex. Remember, we were talking about one particular vertex. So there were 2 adjacent vertices. There are n minus 3 quote unquote opposite vertices. The line segments for adjacent vertices we call an edge of the figure. The other ones we call diagonals. By the way, this is geometry. This is stuff you guys learned a million years ago. It's exactly the same as the graph theory, isn't it? In other words, there's no difference in the concept. It's just when we draw a polygon, do we draw in all the diagonals that are possible usually? No, that's what I'm adding. I'm thinking geometry polygon, now draw all the diagonals. Now, just to make it really, really goofy, could I draw loops outside of the shape to come back? Sure. We can call those different paths. Okay? But this is the basic idea. So there's a ton of geometry in this that's actually quite simple. So this is our introduction. This is our exposure to graph theory. Unfortunately, we don't have time to go further. I was telling Zachary before class, in previous semesters when I've taught this during the whole 16 weeks, I go a little bit further, and for those who've had linear algebra, the next section actually involves matrices. We can do a lot of the descriptions in the higher level thinking using matrices. Oh, it's so cool. But what do you think our matrices look like? What kind of numbers would we have? Well, for those of you who had linear, you know what a stochastic matrix is. I'm going from one thing to another thing and so on. Well, I either have an edge joining 2 vertices or I don't. So the values in the matrix usually would refer to the number of edges. So most of your values are going to be what type of numbers, you think? Zeros, or what if I have loops? Oh, I could have more than one. Most of the time it's zeros and ones. But then we can do manipulation. But if I have 2 paths, right, that would now mean I have 2 edges joining any particular vertices. So the top row might be vertex 1, 2, 3, 4, 5. The bottom, then the columns would be 2, 3, 4, 5, and then the numbers would be the edges joining them. And then there's a whole bunch of cool stuff. I'm going to leave it at that. Sorry, that's as far as we go. Okay, so that's, in a nutshell, that's your exposure, not your mastery of graph theory. Now let's talk about the exam. I'm going to continue recording because there are a few missing bodies here. The practice test is really long. I did that on purpose because I really wanted to hit as many things as I could hit. And a lot of the questions are grouped. Oops. Get over there. Oh, that's perfect. Okay. All right, so this test, we all know, it's all of chapter 9. It's the combinatorics chapter. Are there gimmies in this chapter? Well, there's gimmies in every chapter, but we have to recognize the gimmies. It's funny, before the test, most people would say, well, anything involving pigeonhole principle is a gimme just because there's no calculation. It turns out pigeonhole principle is one of the trickier ones for a lot of folks. It's the only one that maybe doesn't really involve calculation, but involves logic and thinking. And when we start throwing in questions that sound similar, sometimes you're going, okay, I got to pull out my calculator, do some factorials. Oh, it's just a pigeonhole principle question. Right? It's a yes or no because question. So what I did in this case here, I didn't necessarily go by the order of sections. Normally on a practice test, the first questions are from section 1 and so on. What I did was I took questions. The first question is actually from literally 3 different sections. Think about this. I got 12 books on the shelf, or I have 12 books, I'm sorry. How many ways can I put them in order? The number of ways of putting n objects, n distinct objects in order we know is n factorial, we showed that. So the first answer is just easy, that's 12 factorial. One of the first questions we did. Now the second one is how many ways can I'm gonna grab 6 books, put them in my backpack, and then head off to school. Is the answer 6 factorial? What do you think it is?
12 to 6.
Combination or permutation? Or both?
It's common.
Combination.
Does the order I choose the books change my outcome? No. So it'd be combination 12, choose 6. Because then the next question is, I want to grab 6 books and then put them in order on my shelf. Now what's that answer? That's permutation 12, choose 6. Now on the exam, it is very common that you wrote P12, 6, but then on your calculator, you calculated big C. That's the single most common error I see in any class where there's factorials involved. You correctly wrote the right interpretation, but you hit the wrong buttons on your calculator. You gotta hit the right buttons, okay? I don't give you full credit for just telling me it's 12 choose. I wanna know, did you hit the right buttons as well? Because the second answer is a combination, the third answer is a permutation, and that's the most important part, but also hitting the right buttons, because a lot of times we switch them, don't we? I forgot which one was which, okay? Now, on the dice roll, I believe I gave I believe I put all dice roll questions kind of together, and then I went ahead and put a dice roll chart. Because I know all of you would take 5 minutes to make the dice roll chart. So I just put it on your test, just to make life easy. I didn't do it on the practice test because you're not being timed, okay? What's the probability of the sum is prime? That is a union question, isn't it? How do you know it's a union question? Well, if I add up the dice, what outcome or outcomes am I referring to? The sum of what? 2 or 3 or 5 or 7 or 11, and I would simply add them up because there's no overlap. That makes it fairly easy, okay? But it's an or because it's this or this or this or this or this, and we know the probability of an or the probability of a union is the sum of the individual probabilities minus any potential intersection, but the beauty is there's no intersection here, is there? I asked a question on the test, or excuse me, on the quiz that's more similar to problem 5. Now I'm asking for the sum as a multiple of 2 or 3. Easy. Let me take all the multiples of 2 and add it to all the multiples of 3. But what about the multiples of 6? I just counted them twice, didn't I? Oh. So what some of you are guilty of doing is you're actually going to the dice roll and writing down every single outcome that works. That's okay, but that can be really long-winded, can't it? And I can still miscount. It's easier to say, how many of them are multiples of 2? 18 out of 36. How many are multiples of 3? 12 out of 36. How many are multiples of both? I mean 6 and 12. That would be 6 out of 36. So it'd be 18 plus 12 minus 6 out of 36. That's a more efficient way than to actually go and count each individual outcome. That's not incorrect. But as we've seen in this class so far, we always start small and we write down the outcomes when it's small, so we understand where our answer came from. But the moment the calculations start becoming big, I mean, let's face it. I have 12 books, let me give them all names. Now let me write down all the ways I can put down, really? Your answers are in the thousands. No, you're not gonna write them down at this point, you're gonna do the calculation. What's the probability the sum is at least 7? That means 7 or more. This is what I do on the dice roll chart, I just circle, right? Yes, I can write down the individual probabilities, or I can just circle them and say, okay, how many? That's easy. Because now the next question is, it's a conditional probability, which was the last lecture. What's the probability the sum is at least 7 given that one of the dice is a 5? Would you say the probability went up or down?
Oh,
Down.
Say up.
When you add criteria, it goes down.
Well, maybe. If I know one of the dice is a 5, then in 5-1 and 1-5 are the only rolls I would be excluding. In other words, it's going to be true most of the time, isn't it? In other words, in this case, the probability went way up. And so what would it do on my dice roll chart? I'd circle only the outcomes that had 5s, or it's a simple quotient of probabilities. Both are correct. On the key, I put the quotient of the probabilities. Okay. Again, so you guys get the idea here. There are no problems that are long. It's all about correct interpretation. That's really everything. So the next one, Social Security numbers. No restrictions. This is literally how many Social Security numbers are possible? 10 to the 9th power. And by the way, there really aren't restrictions on Social Security. I always have people tell me there are, and I'm like, no, they're not. They're phone numbers and stuff. And I always get the, well, you can't start with a 0. No, wait, you know what percentage of Social Security numbers start with 0? Exactly 10%. Everybody born in the Northeast, my wife, the northern eastern part, New England, that's all, they all start with 0s. Period. I mean, that's not up for debate. That's, the country is sectioned off. California, because we're so big, we have more than one starting number. Yikes. That's scary. Mine starts with a 5, and I was born in California, you know, a million years ago, a couple of millenniums ago. All right, no repeated digits. Go back to question 8. Can you consider question 8 a permutation?
No.
Are you sure?
Yeah,
And you kind of could. You could kind of do it because 9 is 9 a permutation? I'm making you do a different number each time. The first one's not really a permutation because I can use the same thing over and over again, but the form, so think of the first one as putting 9 slots. You say, how many choices for the first? 10. How many for the second? 10. I mean, in this one, it's 10 for the first now, 9 for the next, 8. So I can do it that way. Did anybody do 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2? Yeah, or how about permutation 10, choose 9? That'd be faster. You're gonna get the same answer, you're just gonna get there a lot faster. Now, you're in the millions, aren't you? How many millions? Permutation 10, choose 9 actually is 10 factorial. And what is 10 factorial? It's a lot. It's over 3.6 million. Wait a minute, what was the first answer?
Billion.
Which is
1 billion.
a billion. Oh. That's quite a bit more. That's almost 300 times as many outcomes, right? Oh, so putting restrictions really lowered the number. Now, how many Social Security numbers can be formed with at least one repeated digit? Did you do a long-winded calculation here? Or were you lazy? What is the answer to 10 in words, not numbers? 8 minus 9. Because what's the question? What's 9? No repeated digits. 10, at least one pair of numbers is repeated. Oh, those are complements, aren't they? They've got to add up to the answer to question 8. That's the kind of thinking we've got to be able to do to recognize, oh, that's the complement. And this is the at least one type of problem. We love at least ones, don't we? Because it's always the whole minus the none. Okay, but that's one that's going to stump a lot of folks because they don't realize everything's right in front of them. Don't do a long-winded calculation on that one. Okay. Going to roll the dice, different dice roll question. I've introduced a new word, rollowing. I think I fixed it on the key. All right, I'm going to roll a fair die 4 times. Fair die, that means the probability of rolling a 6 is what?
Depends on how
One-
many sides the die has.
A die. Well, a die by is, yeah. I mean, if it wasn't 6-sided, I would kind of have to tell you it was a different side. Yeah, the default would be a 6-sided. The universal default in a probability scenario is always it's fair. But couldn't we ask a question of an unfair? Couldn't we ask a coin flip question where it said, the weighting is 60-40 or something? Is there anything wrong with that question? No, in fact, it's a great question because it makes it easier to understand bigger things. If everything is exactly the same, sometimes it overly simplifies it. I have a fair die. If I didn't say fair, you'd probably have to assume it's fair. So the probability of rolling an outcome of 6 is simply 1/6. I need that value. By the way, if I said it was a 3, it's still 1/6, isn't it? Because it's just one side. Now, I don't want to roll any 6s, so what's my answer in words?
Not rolling 4 times.
So you're gonna not roll a 6 4 times in a row. Well, what's the probability of not rolling a 6 one time? 5 out of 6. So what is it gonna be the next time? Different? Well, if I have a computer chip in my die, maybe, but I don't have a computer chip in my die. It's not keeping score. So it's gonna be 5, 6 to the 4th power, that's it. Therefore, what's the answer to 12?
5, 6 to the 3rd times 1/6 times 4.
Well, okay, let me do this. What's the answer to 13?
1 minus 5, 6.
1 minus. So what makes 12 trickier? I have to select the slot that I'm going to roll the 6 in. How many ways can I do that? See, 4, you could say 4, choose 1, or just say 4. Okay, let's say it was that slot. Now the probability of rolling that 6, and then the other not being 6s, I don't know, Samuel, is this what you said? Did you say the 4 in front? So that's the answer to this one. Okay, now, if you can reduce the quotient, some of you guys don't realize you have a fraction key in your calculator, and some of you are giving me answers that are bazillion over another bazillion, and the answer is 1/3 or something. I'm getting ridiculously large quotients when the answer actually sometimes simplifies to a really small fraction. If it simplifies to a small fraction, don't do any work. You have a fraction key. The fraction key automatically changes it, and the beauty is you're never going to get a mixed number, are you? You're going to get a nice number. Now, what if it is an extremely large numerator over an extremely large denominator? That's when it is totally acceptable to give a decimal approximation, because let's say my reduced answer is still, 5 digits over 6 digits. I don't think any of us has a feel for the size of the value. So there, by the way, there's an absolute in all math and science classes that's never changed in the history of the world. You never give an approximation of the answer until after you've given the answer. Some of you give me decimal approximations of, there's no answer. No, the answer to every probability question is a quotient. It's legal to give a decimal approximation of that quotient, especially if the quotient's not a useful quotient. Okay, that's okay. Not useful would be the numbers are just too big to interpret. But if my answer is 1/3 or 3/7, no, that's the answer. The other thing is, you can't give a terminating decimal to an infinite decimal answer. That is incorrect. That's called an approximation, and that is not the answer. It's a decimal approximation of the answer. The answer is the fraction. If your answer was square root of 2, you don't write equals 1.4 because it doesn't. That is not true. Okay? Squiggles, you have to know, there's no part of this course that you've ever used. Squiggles means asymptotic, and there's nothing we've done that's even related to that. That's a Calc 1 concept that doesn't apply here. If you're doing a decimal roundup, there is only one symbol. It's the same symbol that's existed for about 100 years, just the ability to do it didn't exist till the 80s. That means it's an infinite, non-repeating decimal sequence, and you're running. You never round fractions because you can always report the repeat. I actually had in this class, somebody wrote, the answer was 1/3, and I got 0.34 as an answer. Somebody actually did that in this class. Instead of 1/3, they said the answer was equal to 0.34, which is really interesting mathematics. Not sure where you got that one. Now, if you're going to give a decimal, give 0.3 with a bar. At least say it correctly. But don't tell me that an infinite repeating pattern is equal to a terminating decimal. And in most cases, the last digit we wrote wasn't even a correct rounding. 2/3 is not 0.6. Not on any planet. That's 3/5. 2/3 is not equal to 3/5. Okay, so that we are writing correct numbers. We're doing terrible on the decimals sometimes because we don't know what to do with the decimals. If it's ridiculously large, I would always calculate the decimal because I want to get a feel of the size of my answer. Has anyone here run into a problem that we've done in class where your answer actually required scientific notation because it was so ridiculous? I don't think we've had any that big or that small. Is it possible to have something big? Yeah, we did an example with a slot machine. If I give you a slot machine question, I said, pull the slot machine 10,000 times, you're gonna get some ridiculous decimals and answer. Yeah, that's totally okay. because your calculators wouldn't be capable of giving a fractional answer. You know, that's when it's totally acceptable. Also, what if the question itself only involved decimals? Do we have any questions like that? I believe we do. Hold on. Oh. No, right here. This is the question. I didn't give you any numbers. I gave you only percentages. Now, is it okay to change 60% to 3/5? Yeah, but leave it as 0.6. There's no advantage to changing it. Later, when you give a final answer, there might be an advantage to changing it. But I would leave it as a decimal throughout this problem. So let's go back. Everything on here is fair game. Now, this is one of my favorite types of questions. It is safe to say that almost every problem on the exam is probably 1 minute or less, if you know the correct interpretation. You have 2 hours to do a test that quite literally you could all finish in 30 minutes. I really, really don't want you to finish in 30 minutes because you're gonna have errors all over the place. You know, you gotta check. And the errors will not be calculation errors in that you added or multiplied badly. It will be errors that we did the wrong calculation. In other words, we did a permutation when it should have been a combination. That's the more likely error. So I have a group of 15 people. What's the probability at least 2 have the same birthday? We now know how to do that. And I just said, it's 15 people. So there was a formula. And by the way, it's legal to write down that formula. Remember what the formula is? Well, what's the probability that nobody has the same? That'd be a permutation. 365 birthdays. Choose how many? 14. Because the first one, oh, did I say that right? Oh, I'm sorry, no, 15, I'm sorry, because you're subtracting 40, yeah. That's the number. What's your denominator? Well, 365 raised to the, remember it's going to be 365 over 365 times, 364 over 365 times, all the way down. Yes, it's legal to write all the fractions all the way down and enter them into your calculator. Now you've made this a 10-minute problem. No, just use the permutation key. And since I said at least 2, you're now going to do 1 minus that number. Agreed? 2 people were born in the same month. Okay, so now I'm going to do permutation. Wait a minute, that's not going to work, is it? Because there's only 12 months, I'd be doing 12 minus 15. That's not going to work. I have 15 people. What's the probability at least 2 were born in the same month?
0.
1. By pigeonhole principle. Oh, the moment I have more than 12 people, I've guaranteed that at least 2 people have to. By the way, don't confuse that with at least 2 people have to be born in March. No. We're not saying a particular month. You could have an infinite number of people and nobody's born in March. I just said 2 people born in the same month. Once I have more than 12 people, the pigeonhole principle. See, what I meant before, this is where we get confused. We go, oh, there's no calculation here. That's straight up pigeonhole principle, and that's what we have to recognize. Now, how many combinations of birthday months are possible?
26, choose 15.
How'd you get that number?
15 plus 12.
Well, how many months are available? There's 12 months, so that's my n. Do we have to have repeats? Yeah, it's not that I'm allowed for, I have to have repeats. Could everybody be born in the same month? In theory? Yeah, could I have like 5 in 1 month, 3? Oh my gosh. So this is simply the R combination with repeats. Now, where I've found people get in trouble on this one is you understand the big picture, but the N and the R. Regardless of how many people I have, what's the one thing that can't change is the number of months available. That's got to be my N. The number of people involved is the R. Normally, R does not exceed N. We know that, but it can in the repeats. So if I said I have 100 people, I have 1,000 people, that's my R. So remember, it's N minus 1 plus R, choose R. So Samuel said, I think you said, what, 26, choose 15? Now, if you recognize the problem, you're writing down the combination, you're giving me the answer, I mean, literally, 30 seconds, if I recognize the problem. I might have to come back to that one because I didn't realize that's what it was. I like to do this with ice cream also, as you know, okay? I've flipped the coin 10 times. The first two questions are basically the same question. You all agree with that? At least 7 means 7 or 8 or 9 or 10. The next one's at least 3, so 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. Wait, is there a faster way to do that?
One minus.
That's when you'd want to use the complement. You never, ever have to use the complement to answer a question, but you often should. The rule of thumb is if the calculation for the complement is smaller than the question, then do the complement. I said at least 7, 8, 9, 10. Remember, there's 11 outcomes, 0 through 10. So now I said at least 3. The only ones I'm leaving out are 0, 1, and 2. Way faster. Go 1 minus that sum. Otherwise, you've got to do 8 calculations. And there's no shortcut. You actually have to do the calculations. So I would do a complement. All right, I love this one. This is the gambler's folly kind of question. I'm going to flip a coin 10 times. What's the probability the last toss is the tail? 0.5. Does it matter what the first 9 tosses were? No. So this is the question I love asking at higher levels. I'm going to flip a coin 10 times. What's the probability all 10 are tails? The answer is 1 over 2 to the 10th. Or just say 1/2 to the 10th. I'm going to flip a coin 10 times. What's the probability that they're all tails given the first 9 are tails? That's what this question is. 1/2. Because it doesn't matter, you're only doing 1 flip. Or if you used conditional probability, you're still going to get 1/2. Isn't that cool? So that one throws people, wait, wouldn't it be really small? Not if you've already done the 9 tails. Everybody got that? So it starts over with each flip. I love that question. In a small town of 17,500 residents, must 2 people have the same 3 initials? So think of your 3 initials. I'm assuming you have 3. You know, I've met people that have 4. I've met people that have 2. And I don't know what their parents were thinking. You have 4?
Yeah.
Are you talking about a hyphenated name?
No, I have 2 last names. So.
That's crazy.
Yes.
And I imagine it's always a problem with the IRS and the DMV,
I have
right?
a special form on all my DNA.
The only thing worse is when women get married and they change their last name. I can tell you, my wife, oh my God, because she was in college. Yeah, oh my gosh, the legalese. Oh, by the way, anybody get the Real ID? I did it during the pandemic. So I went to the DMV. You guys did it where you waited in the line. The line itself was more than a half mile long because you had to have 10 feet between people, and there were hundreds of people in line because you couldn't make appointments. And I'm in the line and I'm bringing everything, including like gas and electric bills and all this to prove who I am, because now it's I'm not the person I was apparently before. So we get there and do all that. My wife, same thing. She had to bring a marriage certificate and a birth certificate and like 3 other things that I didn't, because they didn't believe who she was because her marriage certificate has a different name than her birth certificate. So you talk about hoops having to jump through to get the Real ID because she had to prove who she was because her birth certificate has a different last name. The absurdity of this, so her marriage certificate wasn't enough. Now it was bank statements and social security. I mean, it was so absurd. Yeah, so the 3 initials, I'm going to assume you all have 3 initials here. And you all live in this town of 17,500. And we're going to make it really easy. Mandy, what are your initials? Just
RH.
MRH?
Yeah.
You're no longer Mandy, you're just MRH. That's, I'm MJ Reed, in case you want to know. That we're just going to go by initials. Any chance we have a repeat in this town? That's my question. Ooh. How would I know the answer to that? Do I have, well, no, I'm sorry. We could all have the same first 3 initials. The question is it possible that we all have different, or is there a situation where we have to have 2 of the same? How would you answer this question?
26 cubes.
Okay, 26 cubed represents what?
Pool of all possible.
Good, that's all possible. How big is 26 cubed?
Bigger than this.
Slightly bigger than 17,500. Therefore, it is mathematically possible that everybody in this town has different initials. What if it were 18,000 people? 26 cubed is somewhere between 17.5 and 18, I believe.
Yeah.
I believe that's how I designed it.
17,576.
So we just make it. So the answer is no.
I thought it would be.
It is not absolutely necessary that 2 people have the same. It is actually possible because 26 cubed is slightly bigger than the number of people. it is possible that every single person has different 3. Now, at what point, 26 cubed is 17,576. At what point is it absolutely necessary that at least 2 have the same?
17,577.
Once I have that 17,577th person in the town, now pigeonhole principle guarantees there's a repeat. Pigeonhole principle does not guarantee a repeat. In fact, by the pigeonhole principle, I don't necessarily have to have a repeat. Now, in actuality, if we did the calculation mathematically, this is like the birthday problem. If I've got this many people, what's the probability that no 2 people have the same? Microscopic, but it's not 0. It's small, but it's not 0. That's the key. All right. Number 21, hopefully you've got kind of good at this one. Again, this confuses people. N is what? 5. There's only 5 slots. I said positive integers. That's a trick question. That means every slot must have at least one. Before we did non-negative. You like that better. But I can't have zeros. So what do? I have 30 ping pong balls, and I start by putting 1 in every slot. Now I need to distribute the remaining 25. So I'm solving a different problem now. And the way I'd rather you rewrite it as, now I'm solving y1 plus y2 plus y3 plus y4 equals 25, where my y's are non-negative. You can't say x1 through x5 adds up to 25. That's a completely different problem. You can't use the same variables and a different number on the right side. Does everybody understand that? You have 2 completely separate problems. But if I said, well, let me distribute 1 in each position. Now let me add up the y's, and they have to add to 25, and now the y's are non-negative. So now my n is 5, my r is 25, and it's a r repeat. So 5 minus 1 plus 25, choose 25. This one here probably is the trickiest for a lot of us. There's nothing about the calculation that's hard, it's recognizing it. Now 22, that's just straight up binomial formula. That's supposed to be easy. You got a calculator. Now you're going to have a really large number, aren't you? By the way, is there a coefficient x to the 8th y cubed?
Yes.
Yeah, because it's the first one to the 4th power, second one cubed, and that's where your 7th power comes from. So yes, there is one. 23, I love that question. I love questions of this nature. That doesn't look possible, or is it? There's 2 ways I can ask this question. This I said, prove it, so you already know what the answer is. Or I could just say evaluate it, in which case you got to get that answer. Anybody know what the trick is?
3
Oops.
Okay.
The trick is doing this. And now employing the binomial theorem, so your answer is what? In the end, 3 plus 3 to the end. I love that problem because it's so cool. It's so simple once I understand how to do it. Y'all agree on that one? If I know how to do it, it's simple. Oh, if I know how to do it. All right. Fair game. What makes something a fair game? If the expected value is 0. That's it. It has nothing to do with, well, I played the game and I think it was fair. We played a basketball game today, and I think the referees were very fair, so it was a fair game. No, that's not what it means. Fair game simply means the expected value is 0. So regardless of how many times you played, over the long term, you're not expected to win or to lose. A positive expected value means you should win in the long run. Negative is you should lose in the long run. It doesn't mean what's going to happen each time you play. Think of it more like a long-term average. Or if a whole bunch of people are doing it, what's the average outcome of everybody? That's a simpler way to think of expected value.
Oh, I was just gonna say, because it wouldn't be a fair game if your expected gain is positive, right?
Yes.
It should just be 0.
Yeah, because if you and I are playing a game and the expected value for you is positive, then the expected value for me is the negative of that value. So over the long term, you should win most of the time. So in the problem like this, how do we figure it out? Well, you find what are the possible winnings. You are paying $10 to play. So don't think of it as winnings, think of it as outcomes. So I won $4. Well, winning $4 isn't an outcome. If I paid 10 to play and then I win 4, I walk away -6. That's the outcome. The outcome is neither 10 nor 4. It's 4 minus 10. So then the second outcome would be 7 minus 10, and the third outcome would be 20 minus 10. And each of those outcomes has a particular probability, which is easy to calculate. And then I add up the probability times the outcome. I add them all up. What did you guys come out with? Anybody?
-2.
It's -2. So it means if you play this game a lot, on the average, you're going to lose $2 every time you play. Or we all play this game exactly one time. The overall group average is we lost $2 per person. Will somebody win? Of course, but more people are going to lose than are going to win. That's all that means. Okay? Now, I would strongly advise you on a problem like this. You don't have to. Draw a Venn diagram. You don't have to. But if you don't draw a Venn diagram, it's very possible you misinterpret the values. And a Venn diagram, I'm a big fan of this. Okay? You never have to, but we find that when we do, it probably makes the answer easier to see. Plus, if I do the Venn diagram, there are certain problems that I may not actually have to calculate. The answer's already sitting in the diagram for me. So what are my categories? So what do we got? Exercise, charger fan. So we'll call E, exercise, C, charger fan. Now, where do you always start when you're filling up the picture? Start with the intersection. What's the intersection? 0.21. Now let's work our way out. What percentage of people exercise? 60%. So what's out here? And 40% are still Charger fans, so what's out here? Now, what have I got so far? If I add up all those numbers, because, by the way, these three pieces are disjoint. This 0.39 represents people who exercise and are not Charger fans. These are exercise and Charger fans. These are Charger fans and don't exercise. These are three mutually exclusive pieces. Agreed? So if I add up those probabilities, what do they add up to? 0.79, which means if I do this, that might make some of this easier, not all of it. A Charger fan is chosen at random. I'm sorry. A Charger fan is chosen at random. What is the probability that they exercise? 0.21 over 0.4. Everybody got that? Why? Because my sample space changed to only Charger fans. So my denominator is the probability of Charger fan only. My numerator is the probability of the intersection. This is conditional probability. Second question. A regular exerciser chose exactly the same question in reverse. Now I'm choosing from this, so my answer is what? 0.21 over 0.6. Did I have to draw the picture? No, I got that right from the information given. But if I look at the picture, sometimes it's easier. Are the events being in E and being in C independent, yes or no? There are three ways you could answer this question. So let me show you now, what are the three ways? The probability of being a Charger fan given you exercise regularly was 0.39 over 0.6. The probability of exercising regular given you a Charger fan, you said was, oh, I'm sorry, not 0.39, sorry, 0.21 over 6, so was 0.21 over 0.40. And this is not equal to the probability of being a Charger fan, is it? This is not equal to the probability you exercise regularly. So exercising regularly given you're a Charger fan is not the same as exercising regularly by itself. Same here. In both of the cases, you could make the conclusion, or a third way of doing it is what? The probability of being in the intersection is not equal to the product of the probabilities. All three of these are correct reasons for the outcome. It wouldn't matter which one you said. After the first question, a Charger fan is chosen at random, find the probability they exercise regularly. This value here is what is this value here? 0.35? And probability of being a Charger fan was 0.4. So this is not equal to the probability of being a charge event. So you're done right now, they're not independent. Or I could do this. Everybody cool with that? By the way, don't do all three. So if I said, are they independent, you'd say no because, and then just give me one of those reasons. I'm just saying, they're all three were valid. There is no other reason. And I always laugh at the stats class. People will argue, well, everybody knows that, being these are independent. You're trying to give me an argument. No, the numbers tell me. Is there any way I could redesign this question so they are independent? Yeah, I said 21% do both. What if, instead of 21%, what if that was 0.6 times 0.4? 24%. Yeah, what if the question was 24%? Then this would have equaled 0.4. This would have equaled 0.6, and these would have been equal. Oh, so if I had changed the probability of the intersection, I could have made it so they are independent. That's all I would have needed to do. Everybody understand that? So if the probability of the intersection had been 0.24 rather than 0.21, then all three of these would have been equals. And again, only one of them is needed to justify your result. Okay? We're almost done. This is not a graph theory problem, although it seems like one. This actually came from the chapter 9. I've got an octagon, an 8-sided figure. How many line segments can be drawn using the vertices as endpoints? We already know the answer to that. What did we say earlier? I want to draw a line segment. Remember, the edge and the diagonals, I'm counting how many of both. So from each vertex, how many line segments can I draw? Exactly 7. We did this one already in class. And I have 8 vertices, therefore exactly, excuse me. Sorry. So how many line segments could I draw exactly? 8 vertices, and each vertex I can draw 7 line segments. So what's the answer? Is it simply 8 times 7? It's 8 times 7, right? I'm leaving with my left eye.
8 times 7.
It's 8 times 7, right? Because when I draw this line segment, I count that as one line segment coming out of this vertex. But I also count it as one line segment coming out of this vertex, don't I? Oh. So is it 8 times 7?
2.
Over 2. Over 2.
Okay.
Why? Because each line segment is joining 2 different vertices, and out of every vertex, I can draw 7 line segments. But every line segment is connected to a different vertex, which means I counted it for that vertex also, didn't I? So if I said, what's the total degree of the vertices? It's 8 times 7. That would be the degree of the graph. But how many edges would there be? Must be half. Why? Because the degree of the vertices was exactly twice the number of edges. I don't need the graph theory for that. That's more of a common sense thing. If I'm counting this as an edge coming out of this vertex, the same edge is also being counted coming out of this vertex. So every edge got counted twice. So the 8 times 7 over 2. How many triangles can be formed using only the vertices? Ooh.
112. Choose 3.
Good. A lot of you are thinking of the picture and drawing it. By the way, whatever you do, don't draw it. Draw the line segments and then count your triangles. That's way too long of a problem. Why is it 8 choose 3?
So you got 8 and you're choosing 3.
I have 8 vertices and I just need any 3 of them. And does the order matter? No. And will I repeat myself? Will there be any overlap? No, because once I chose the 3 vertices, there's only one triangle that I'm looking at. And in both of those 3. If I pick a different 3, there's a different triangle for each 3 that I pick. Does that make sense? Yeah, after the fact, it makes perfect sense. Before the fact, maybe not so much. How many triangles can a given vertex have?
You choose 3 over 8 times 3. Well, sorry.
That might be right. That sounds too complicated. From any given vertex,
7 choose
I only need 2 more, and how am I choosing them from?
the other 7.
The remaining 7, so what should my answer probably be?
7 choose
2. From any one vertex. I didn't say the total number, I said from any one vertex. Now, from any one vertex, he says there's 7 choose 2. What is that number? 7 choose 2 is what? 21. What was 8 choose 3? 8 choose 3 was 56. 8 choose 3 was, is that 56?
Yes.
Okay. 7 choose 2 is, we said 21. So from any one triangle, sorry, what was the question? How many triangles do pass through any one vertex? So if I pick that vertex, how many triangles? Well, I need to select the other 2 vertices. Does that make sense?
Because there's 7 vertices.
There's 7 more
So
vertices.
only one. And you need 2 others.
I just need to, yeah. This is a combination question. Using the polygon just give you impetus. Would it matter? I could have used books. I could have used something else. So don't worry about that part. But I like throwing this one in there because it's a nice crossover to the stuff we did today. Now, what I didn't put on the practice test were any proofs. There aren't that many versions of the Pascal's theorem that we need to see, you know. Any proof involving factorials, right now most of you are doing a pretty good job on those. It's like, I just do the factorials and spread them out. Now, what do you need in terms of formulas and such? I'm hoping you guys know permutations, combinations inside and out, but the binomial formula might be what, a plus b to the nth power, what does the expansion look like? That might be one you want to write down, the summation of, because I'm going to ask you to calculate a coefficient. That's a fairly simple thing. I might say write the first 3 terms or something. That's a fairly simple thing, but I don't want you to multiply it out. I want you to use the formula. R repetitions, right? Combinations. What is the formula? Anybody know? N minus 1 plus R, choose R. Doesn't matter if R is bigger than N. With repetitions, R could be literally limitless. Now, when I asked that question, I think the way I did it before was, I think I used sodas or something, and I said there's bazillions of sodas on the shelf. What does that number mean? I'm not going to run out. I'm not going to ask you a question where you're going to go in and you're going to buy 100 donuts, but they've only got 5 of these and 6 of those and 10 of those available. That's a very complicated problem. So we're going to say this donut shop has a warehouse where they're storing, literally an infinite number of donuts. We're going to ask that question. Simply means you're not going to run out. Because if it's possible to run out, it's a very different problem. Everybody understands that. That's really a tricky problem. I would write down Pascal's formula. That's a simple one, but it may come up that you want to use it to do a calculation and you want to keep it simple. Most of it's just thinking, being able to think. There is a formula for conditional probability. That one you might want to write down. The probability of A given B is the probability of the intersection over the probability of which one? B, because you've changed the sample space to B and B only. That's why it's probability of B in the denominator. This is not hard to use, but if I forget it, I might mess that one up. Any questions? You guys are set. Yeah.
Was there a problem that was like a dice, but the sum was more than 1? I'm trying to remember. I thought I saw that on the grade.
Yeah, we did one where we went.
But it was looking for the expected value. I didn't actually.
Oh, on the quiz I asked you expected value one.
I thought there was one on the practice test that asked about it.
There was, you skipped.
Thank you. You're right. I went too fast. Number 24. 3 fair dice are rolled and the sum is computed. Now, first of all, if I have 3 dice, how many possible, dice rolls are possible? Well, with 2 dice, it was 36. So with 3, what is it? 6 cubed. 216. I'm calculating the sum. Now, what are the possible sums with 3 dice? What's the smallest sum I could have? A three-eyed snake, right? A train with 3 boxcars. Would you agree it's 3 to 18? Okay? Excuse me. The result can be any integer, so what I would do is, I would do each of the calculations. It'd be kind of tricky, and all of them are over 216.
Could you,
It's not as, I'm sorry?
could you instead just say that the dice don't influence each other and each one has an expected value of 3.5, so 3.5 times 3 is 10.5?
Yeah, but you're not looking at the outcomes if you do it that way, though. So if we're looking at the outcomes.
Do you have to?
Well, no,
write
but
it all out
the
on
whole point of the
test?
problem is, if I look at the outcomes, what are my possible, 3 to 18, and the first one's gonna be 1 over 216, what's the probability of an outcome of 4? Well, there's only 3 ways I can get that. Now, if I go back to my regular dice chart, this is where you can be a little bit clever. How many ways was there to get each? All of them were combinations. It was 2 choose 1, and then 3 choose 1, and then 4 choose 1, and 5 choose 1, and so on. How many ways can I get a sum of 4? There's only 3. How many ways could I get a sum of 5? Now I possibly, in other words, if you look at the key, I did this on purpose. But now, in the end, when I do my computation, okay, Samuel's correct. What is my expected value going to be?
10.5.
Hold on, let me. Oops, this is. I'm not going to ask you something, by the way, that's got this much involved, but I want you to just see what it looked like. It's kind of it's a cool problem. You guys just did an expected value for me for an odd die. What, it was an 8-sided die?
Yeah,
Is there such a thing? Yeah. Anybody seen multi-sided die before? Yeah. Well, there are games that use those.
I think it's gonna be 7-sided.
The equipment was 7-sided?
Yeah. which
That
is-
one's a little harder to construct, just so you know.
How would you make it?
7 sides is hard to work with. So these are all the numbers. I'm throwing that out there, just because it's a cool question. I'm not gonna ask you this because the individual probabilities would just take too long. But in the case where there was a multi-sided die and I wanted the expected value, it's really the same problems that we already know, but we never thought about that. What is the expected value if you just roll a fair pair of dice? What's the expected sum? Well, let's see, I can get a 2 times 1 over 36, 3 times 2 over 36, 4 times 3 over 36. If I add all those up, it's going to add up to exactly 7, which, like Samuel just pointed out, each die has an expected value of 3.5. Now that's weird. How can a die have an expected value of 3.5? Because each side has a probability of 1/6. So I'm taking 1 times the 6 plus 2 times the 6 plus 3 and so on, and that adds up to 3.5. We don't really think of it that way, do we? That's not something that would enter our minds with, oh my gosh. So I'm going to have you roll a die 100 times and write down all the numbers you get. Now average them all up. Your answer should be really close to 3.5. Similar, I'm going to have you flip a coin 100 times, count the tails. Your answer is probably going to be really close to 50. It's the same mathematics, exactly. Because it's taking the n times p. Okay? All right, let's stop. So go ahead and, this is a little longer than usual. I'm going to kick you guys out of here.